Hi everybody, I'll be presenting on the ICP MS, which is inductively coupled plasma mass spectrometry, and this instrument is a powerful tool for elemental analysis. The ICP-MS is an analytical method that is used to measure elements rather than molecules or compounds. The first ICP-MS was introduced by SciEx at the Pittsburgh Conference or PitCon in 1983, and it was introduced as an improvement over previous methods like atomic absorption spectroscopy, graphite furnace atomic absorption, flame photometry, and inductively coupled plasma optical emission spectroscopy. Now, many of these older methods have limitations in detection limits and multi-element analysis compared to the ICP-MS, which allows multiple elements to be analyzed simultaneously in a single analysis with very high sensitivity, short analysis times, and simple sample preparation. And also, you only need a very low sample volume for analysis. The ICP-MS is widely used in many industries where accurate measurement of trace elements is required, such as food, mining, and metals analysis, semiconductor manufacturing, geochemistry, and petrochemicals. Talking about the instrumentation, the ICP-MS is composed primarily of an ion source, which is the ICP torch, a mass spectrometer, and a detector. It uses an argon plasma to break down molecules into atoms, which are then ionized in the plasma. The high temperature plasma typically produces singly charged cations. In a normal operation, you introduce samples as a liquid into the nebulizer. The nebulizer then converts the liquid sample into a fine spray with the aid of the argon gas, and then a single quadruple mass analyzer guides and filters these ionized atoms according to their mass to charge ratios until they reach the detector. Now let's take a look at the analytical power and practical constraints of the ICP-MS. In the ICP-MS, element ionization is independent of the chemical structure of the compound containing it, so you don't have to worry if you are looking at gold and the gold is in uh, a complex compound. It does not matter when you analyze it using this instrument. And also, any sample that can be dissolved or acid digested to produce a liquid can be analyzed. You can analyze nanoparticles and organic solvents. Nanoparticles can be easily acid digested to be analyzed using this instrument. And also because it has a mass spectrometer, it can be coupled to chromatographic separation devices like HPLC, and also it's capable of separating and analyzing the individual isotopes of elements because it has a mass spectrometer in its setup. And also it can measure most elements at amounts below zero point 0.1 ppt and concentrations up to hundreds or thousands of ppm. On the downside, the ICP MS is pretty expensive. It has a very high cost of equipment and operation, and you have the initial lab setup expenses. Because it's a mass spectrometric method, it's susceptible to matrix effects, and also you need a high level of operator expertise to use this instrument. For this presentation, I looked at two applications of the ICP-MS, and the first application is analyzing the concentration of metallic elements in the blood of patients with multiple sclerosis. Now, multiple sclerosis or MS is a neuroinflammatory disease that affects nearly 2.5 million people around the world. It involves an autoimmune attack on the myelin sheath in genetically predisposed individuals, and the hypothesis that the researchers had in this study is that metals can play a role in the etiology of multiple sclerosis. Previous studies were also conducted to assess whether metals can play a role in the etiology of multiple sclerosis, but they had limitations like small sample sizes, limited elements, and less precise methods. So, in this study, the researchers used 12 metallic elements to analyze whether there was uh, whether there was a link between heavy metal exposure and multiple sclerosis. And also, they used a sample pool made of 30 multiple sclerosis patients and compared with 30 healthy control individuals as well. Another reason for doing this study is because heavy metal exposure as a factor in multiple sclerosis remains underexplored. The elements that were analyzed are barium, beryllium, calcium, cobalt, chromium, copper, iron, magnesium, molybdenum, nickel, lead, and zinc. Blood samples were used for this study. They were freeze-dried, microwave digested, and reconstituted for analysis using the ICP-MS. The researchers say that the imbalance in metallic elements could serve as biomarkers because, according to their study, the key findings are that elevated lead levels in multiple sclerosis patients were observed and reduced levels of beryllium, copper, chromium, cobalt, nickel, magnesium, and iron were observed, and there was no significant change in molybdenum, cesium, barium, calcium, selenium, and zinc. They say that the altered metal levels can be linked to environmental and occupational exposure, and also metal accumulation can be there in the central nervous system, and oxidative stress and myelin degradation can also be there because of the altered metal levels in their blood. Um, and they also state that the deficiencies in essential metals like cobalt, copper, magnesium, and iron can contribute to demyelination. Now, demyelination is important because multiple sclerosis occurs because myelin is degraded because of an autoimmune attack in genetically predisposed individuals. So, if demyelination can occur, this can also be a cause for multiple sclerosis. However, they acknowledge that further research is needed to establish causal links and mechanisms taking place if metals had a link to multiple sclerosis. The second study is where researchers looked at whether single particle ICP-MS can be used as a screening tool for detecting inorganic nanoparticles in food. Now, this is quite relevant in the current landscape because nanotechnology used in the food industry is rapidly increasing, and there are many food additives that contain particles in the nano range. And we all know that nanoparticles can behave differently from bulk materials, and this raises concerns. In the European Union, there are several regulatory uh, regulations that try to control the use of nanoparticles, nanomaterials in food, such as the regulation 1169 of 2011 and 1333 of 2008. In this study, the researchers evaluated the capability of ICP-MS, specifically single particle ICP-MS, to detect inorganic nanoparticles in food. They tested 13 different food samples, such as chewing gum, coffee creamer, noodles, espresso, to check for nanoparticle presence and distribution. The relevance and the importance of this study is because of all the regulations in place, you need reliable detection and characterization methods like ICP-MS to comply with them. So single particle ICP-MS was used because it's highly sensitive. It detects at nanograms per liter levels and it's element specific. It measures nanoparticle size, number concentration, mass, and the distribution as well. And also in single particle ICP-MS, it assumes that one nanoparticle is detected per pulse. And this assumption is brought upon uh, by working with the dilution and the dwell time. And also in single particle ICP-MS, you can use Poisson statistics to validate data accuracy, and you can detect polydispersed, aggregated, and agglomerated nanoparticle systems as well. According to this study, uh, nanoparticles were observed in almost all the food samples, as you can see in the figure A. And in figure B, you can see which nanoparticle types can be quantified. The key findings in this study is that coffee creamer had the highest nanoparticle count, but only three types were quantifiable. White wine and beer had no quantifiable nanoparticles, and the sources of nanoparticles were threefold. They can be intentional additives like titanium dioxide in food coloring, and they can be present due to environmental contamination like iron nanoparticles from pipe corrosion, and also they can be present because of processing equipment like silver nanoparticles from coffee machines. Uh, the, the the study acknowledges that you need complementary techniques like total ICP-MS and scanning electron microscopy for full characterization and definite conclusions as well. So, in conclusion, ICP-MS and single-particle ICP-MS are powerful analytical tools to detect and quantify metallic elements and nanoparticles in complex matrices. Studies demonstrate a potential link between metal imbalances and neurodegenerative diseases like multiple sclerosis. The presence of engineered nanoparticles in food products highlights the importance of sensitive detection methods for consumer safety. Single particle ICP-MS offers high sensitivity, speed, and element specificity, making it suitable for regulatory compliance and routine screening. However, you need other complementary techniques like SEM and TEM